All right, we're gonna spend 1 hour together here talking about mutation. And just very briefly, mutation is any permanent changes that occurs in your genome, in your DNA. Okay. And these mutations can be as a result of random mistakes that you introduce as you're copying your DNA, or there could be certain environmental factors that will increase the risk of getting a mutation. We talked about some of these things last time: exposure to UV light, exposure to chemicals in smoke, for example, like smoking cigarettes. Right? So these things can sometimes increase the risk of getting mutations, but in the end, mutations are basically permanent changes in your DNA code. And if you change your DNA code, you might affect how the proteins are being made. Now, I'm going to give you a quick note here. Actually, we'll be taking several notes. But here is the quick note for mutation. It's a short one, okay? A mutation, permanent change in your DNA sequence. Once again, this mutation stuff will be on quiz number 4. So make sure you pay attention. And if you don't understand, ask. So mutation can, for our purpose, we're going to be looking at 2 types of mutation. The first one is called base substitution. Base substitution involves changing a single nucleotide. There could be 3 outcomes. Number 1, neutral, or sometimes called silent, because you wouldn't even know about it. Number 2, missense. Number 3, nonsense. I'll explain what they mean in a bit. Just copy it down first. The other mutation is called insertion or deletion. Right? Sometimes called indels. And there are 2 situations here. You are either inserting multiples of 3, so 3, 6, 9, 12, or deleting multiples of 3, or you're not. So if you're inserting 1, 2, 7, 14 nucleotides, that's not a multiple of 3. And the results, the consequences will be different. When it's multiples of 3, you will end up having extra or missing nucleotides. If you're not inserting multiples of 3 or deleting multiples of 3, then you have something called frame shift. which I will explain later as well. These are not the only kinds of mutation that exist, but these are the only kinds we will be learning about. Let's start with base substitution. Okay. Now remember, the mutation occurs at the DNA level. Okay. But to make it easier for you to understand, I'm going to make the change at the RNA level. Because if you change the DNA, your RNA is going to be different anyways, right? Because the RNA is a copy of the DNA, right? And so I'm just making it easier for you to understand by doing it at the RNA level. Okay. So let's do the different types of base substitution. So we have what's called a wild type. Wild type is the is the normal one. Okay? It's the one without the mutation. And we call it the wild type. And let's say we do CAG. CAG. I don't have my codon chart. I gave it all out, but if you have one, you can look up CAG for me. GLN. Yeah, CAG is right here, and it is GLEN. Okay, glutamic acid, right here. So let's do a base substitution. In base substitution, you will change one nucleotide only. Yeah, you'll be asked to do this on the quiz. I'll give you a code and I'll ask you to mutate it to meet certain conditions. So let's say we're gonna change it to CAA. So this is a mutant now. Mutant, that's what they're called. CAA. What's the change? Which letter, which nucleotide was changed? Yeah, the last one, right? That's a change, okay? Can we look up the CAA, please? Same. Still GLN. This is the best kind of mutations to have if you need to have one. Okay, mutations are rarely good, right? They usually cause quite a bit of problem. But this kind of mutation is the safest, so to speak. Okay? Why? Because even though you change the codon, you don't change the amino acid, right? So there's no change in your protein sequence. It's probably not going to have an effect. What do we call these kind of mutation? Choose a name that's appropriate. What do you think? Yeah, this is neutral. Okay, it's not going to do anything. You won't even know about it. Right? It's silent. Remember we talked about how you and I are 99.9% the same? The 0.1% difference is primarily due to these kind of neutral mutations. Okay. We call them SNPs. Right? We'll learn more about SNPs later in lecture 9. Okay, let's do another one. Let's mutate to GAG. What is GAG? What does it code for? Is it GLU? Can we confirm that, everybody? Yeah, okay, I couldn't even find it. Okay, this is GLU. Okay, make sure your writing is not like ugly like mine, okay? Otherwise, the U looks like an N, and then, you won't understand what's going on here. So this is a mistake, right? It's a different one. Yeah. So we call this a missense. Missense mutation, okay? You know what? I'm gonna choose a different one just in case like it gets really messy in your writing and you get confused. Can we do AAG instead? What's AAG? AAG is LYS, right? Okay. Yeah. Not that there was anything wrong with the other one, but I want it to be like this different. Okay, so that is a missense mutation, right? Missense. Good? No? What's the question? Do you understand the first one? This one, we change one of the nucleotide. It doesn't matter. You can take the first one, the second one, or the third one. The point is, after you change it, the amino acid is different. And we call it missense. If it's different, it's missense. That's right. Okay, so look, I don't have to change the first one. I can change the middle one. Instead of CAG, I can change it to CCG. Can you look up CCG? Anyone look up CCG for me? Pro, right? So that becomes GLN to pro, which is also a missense, right? Okay, but you cannot change more than one. Right? The phase substitution is change one thing. All right. No, I'm just changing like mutation. So like you're supposed to copy CAG, but then you made a mistake. Your polymerase made a mistake. Instead of putting a C, it accidentally put an A instead. That's right. Okay? Inside? Okay. Let's do one more. This one is gonna be. I'm gonna also change the first one. And I'm gonna go U this time. Remember, this is supposed to happen at the DNA level. I'm just doing it on the RNA to make it easier for you to see. Okay, what's UAG? So, okay. So this is nonsense. Like everything we learned in the course, nonsense. Now, why it's true? Oh, hurt my feelings. So why is it nonsense? Well, if you have an protein here, amino acid here sequence, okay, let's say it's like this many amino acid long, right? Okay, so normally you're supposed to, build the whole thing and then you stop at the end. But if I have a nonsense mutation right here and it becomes a stop codon, then you will build, and then you hit a stop codon prematurely, and then you stop. You don't make the rest of the protein. You understand? Okay, so that's gonna be what we call like a truncated protein. Truncated means shortened protein. Truncated. Yeah, TRUN. Now, if I ever ask you which mutation is the worst, you have to be careful, right? Because the correct answer is it depends. It depends on several things. Like, do you think a nonsense mutation is bad? What's the answer? Depends, okay? When I ask you, you always say depends, and you explain to me. Now, do you think you might think like nonsense mutation is bad, right? Okay, but look, let's say you have a nonsense here, okay, nonsense. We'll say nonsense mutation A versus a nonsense mutation here, nonsense mutation B. Okay, which one is worse? A is worse, right? Because you're losing like a whole chunk of the protein, and then it might not be functional anymore, right? What if this is a red light protein? The ones that we talked about, like the tumor suppressor gene, right? Then you're losing the red light. That's one hit already. Right? If it happens again, then it might become cancer. Right? Now, if you have a nonsense mutation here, I'm not saying it's gonna be all happily ever after, but it's towards the end. So you are losing one or two amino acid, and that might be okay. You understand? How about missense mutation? You think missense mutation is bad? That's right. And now you're catching on. It depends. Right? So do you know what this is? We talked about this thing multiple times. Oh, thank God. Okay, enzyme. Good. Okay, and what do we call these sites that you put stuff in? Yeah, we can put building blocks in there, but specifically, what kind of sites are they? What is it? You would put the substrate in, yes. No, that's okay. That's okay. Active site. Okay. So let's say I have a missense mutation here, right? Missense 1A, or versus like a missense here. Missense, the whole thing is a protein, right? Okay, missense B. Which one is worse, A or B? A, because A missense, you change the amino acid here, you might end up changing the shape of the active site, and then it will no longer fit the substrate, right? Okay. So as a loose analogy, think of it like this, okay? Like, imagine there's this huge nail, okay? And this nail is gonna get stuck in your car. Is it gonna be detrimental to your vehicle? What's the answer? It depends, that's right, okay? If it goes into your tire, then it's pretty bad, right? Okay, like you might be able to drive a little bit, but eventually you're gonna get flat tire and you can't drive them anymore, right? But if this thing gets stuck in your trunk, sure, it's not nice, okay? But your car is for the most part functional, right? So these kind of mutations, even if it's the same mutation, even if they're all nails, so to speak, it depends on where the mutation occurs, then the results are going to be different. Some are going to be more damaging than others. Are we together on that? Okay. But we can all agree the least concerning kind of mutation out of all the ones I've shown you so far is which kind? That's right. If you have a neutral, it doesn't matter where it happens, you wouldn't even know about it, right? You're probably going to be okay. So these are base substitution, and I hope you understand it. Now I'm going to give you one. How time do we have? No. Okay. So I'm going to give you this one. This is the wild type, the original. I want you to give me an example of silent neutral, okay? Missense and nonsense. Okay, go ahead. Just 2 minutes, okay? Not long. How many nucleotides can you change? One, okay? That's it. Remember that on the test, on the quiz. Yeah, one. Whose lunch is that, huh?
Could you table it?
Sure.
Do you have any more?
I don't have any more, sorry. You know what? Hold on. I'm gonna put it over here. Oh, you have a nice. Thank you. Do you need it back, Annie?
Oh, no.
You have an extra one? But you memorized it or something.
Actually, yeah. That's what
There
it
you
is. Like the song.
It's CYS, right?
Yeah.
Christine? Have it? Oh, yeah, anything, as long as it's silent. So what did you change? UGU. So let's see. UGU is also DYF. That's the only answer, right?
Yeah.
And sometimes there are more than one correct answer. Sometimes there isn't. I need a missense. Okay, now on the test, sure. The easiest way to get a missense is to change the first one. Okay? Silent is usually the last one. Sure, you can change it to CGC. which is yeah, ARG. But again, like that's not the only answer, right? Anyone else have something different? UAU, but you can only change one thing, right? No, yeah, you only change one letter. Yes,
For which one, the missense or?
miss it.
I put AGC.
AGC.
And it's SER.
AGC is SER.
Yeah.
Very good. Right? Maybe one more. Anyone else? UAC. Sure. Yeah. What's UAC? Right. You guys understand?
Yeah.
You will get perfect on that question on the test, please?
Yeah.
I hope so, for your sake. Nonsense. Right? How do we change this to nonsense? Yeah. That's the only way, right?
Wait, so is nonsense always gonna be stop?
That's right.
Okay.
So listen, not all codons can have a nonsense mutation. Right? Not all codons can have a nonsense mutation. I can have like AAA. You can't make it into a nonsense, right? Okay, because nonsense is UGA, UAG, UAA, right? Crystal, we can move on. Great. Okay, I'm gonna teach you so like we learned about sickle cell anemia before, right? If you change one nucleotide, then in this case we have a missense mutation, right? Change it from a polar amino acid to a non-polar one. That's enough to cause severe outcome. Okay, I want to do indels now in insertion and deletion. Now, the ribosome. The ribosome reads codons in triplets, right? 3 nucleotide makes up a triplet. So it's like if we can only read words in triplets, it would be like this, right? So what does the person gonna say? They can solve the fat job, right? So that's fine, right? It's like 3 letters, right? Okay. However, if we delete the B over here, if we take that out, the is fine, but the next 3 letters is gonna be IGC, right? Right, and then ATS. So nothing makes sense anymore, right? By deleting one letter, we change the reading frame. We shift the reading frame, and the sentence no longer makes sense. Right? We call this a frame shift. Right? What if I deleted 3 letters? If I delete 3 letters, that's right. The sentence structure is maintained. Okay, we lost a word, but it's not a big deal. The sentence still makes sense. Okay, and I still kind of understand like most of it, right? Okay, like, but I no longer know about the cat. Like, was it a red cat? Was it a fat cat? Was it a big cat? Like, what is it? We don't know. Okay, but that's okay. The sentence structure is made. Okay, compare the original with this one. What did you see the problem? That's why we inserted an extra letter here, okay? So now, again, the whole sentence structure is destroyed. We have a frame shift. It no longer makes sense. Okay, but deletion or insertion of multiples 3 is okay. And we add the word red, sentence structure is maintained. All right. So last Thursday, I gave you a worksheet. Okay, please take that out. Okay, please take a moment and do the first box. It's exactly what you just did for the quiz. Okay? So go ahead and do that. Please, please, please. I don't have an extra one. I'm sorry. Do I? No. Is it big enough? You want that? Okay, you need to do this. Otherwise, you won't understand it. There is going to be questions like these on the quiz 4. Just 4 more weeks, guys. Hang in there.
Original DNA sequence, that's template.
Yeah, it says template in the question. It's all right. Now, if you get a question like this on the test quiz, chop it up in triplets, okay? It's easier to make mistakes if you don't. Okay, or you can use dash. Please check my work. I'm a little bit out of it. I just realized I didn't give you the exact same chart on the test and none of you complained. So good job. I should have gave you this one, right? I'll do that for the future evaluations. Sorry. It's good. This class not much complaining compared to, previous years. Yeah. And then what's the next one? CYS, yeah. Can I take your word for it? Yeah. All right. And please confirm that's the answer. Confirm. You can confirm your own answer.
Yes.
And so what do we call this one? If it's the original.
Template.
No. Without the mutation, what do we call it? Wild type, guys. Okay, wild type.
Sorry.
That's okay. This is the wild type. All right, now we're gonna look at mutant number 1. We're gonna chop
Saying wild type.
the original without the mutation.
So the template is also.
It's not so much the template or the coding, but like the original DNA before the mutation.
Okay.
It's called wild type. Okay, so we can chop it up, guys. Chop it up. Okay. Can we find the mistake, please? Where is the mutation? You have to compare it letter to letter. ATC. Okay, and what's the change? Which one should I highlight? Yeah, C to T, right? Yeah, there we go. Wait a second, I think it froze. Right here. This guy? All right. So let's write the mRNA sequence. TAC is going to become AUG. ATC, what's ATC going to become? UAG. And the rest are the same, right? I'm not going to write it. You have to write it on the test. I'm not going to write it now. What will be the amino acid sequence? AUG, what is that? Matt, that's the start codon, right? Everybody should know that the start codon is MET. What's UAG? Stop.
Wait, how can you?
Yeah.
How mutate?
So you have to compare the wild type with the mutant, letter by
Oh,
letter.
I'm comparing to the top one.
Yeah, this is wild type, okay? Original.
Okay.
Okay, what kind of mutation do we call this? Nonsense. That's right. This is nonsense. Will there likely be effects? Do you think this is going to be bad? Like very bad or just a little bit bad? Very bad, okay? So will there likely be effect? Yes. Okay, very bad. You have to tell me why as well on the test. Okay, entire protein is gone. Right? We're not making the protein. You just put down the MET and then you stop. Everything is gone. It's like only handing in the first page of your lab report. Very bad. Okay, please try the second one. Okay, do it with a classmate or something. Chop it up first. It's easier to see.
Which one is it? Number three.
Do you find the problem? What? Huh? Good. Huh? Is it more than one? Did you chop it up?
One more.
There's one more?
No.
Oh, you mean like an additional one?
Yeah.
Yeah, what do we call that? We have a name for it, don't we?
Hawaiian. Newsom. Oh, wait, it don't.
No, look at the chart. We have a name. Are you guys okay? Trying to say for challenge? What do we call that? What kind of-
Oh, at the end. Oh, what?
Yeah, symmetry, but extra one. The people say. the full chart.
Oh.
Wait, I don't understand.
You know what it's called?
I think maybe it's saying like.
In the full chart.
Extra missing. But. Wait, so that is called an insertion?
That's
Yeah.
based on-
But it's not like.
But also there's a change with the GA, C.
You found the mistake. It's an extra one, right? The insertion, that's right. Now, listen for a second, please. On the test, if you're trying to figure out what's the problem, you have to chop it up first. Can you watch, please? I'm helping you to do better on the quiz. You chop it up, and you see there's a leftover one. That's a telltale sign that it has been an insertion mutation. Because it shouldn't have leftover, right? Before over here, it's divisible by 3, right? Now you try to divide into groups of 3, you have an extra one. It's definitely an insertion mutation. Okay? And then you got to find where it is. So TAC, TAC, ACC, and then it's not same, right? So this is the extra one. Do you understand? Do you understand why this is insertion and not base substitution? Okay, so we're going to say insertion. And whenever we have insertion, let's see what's going to happen. Okay, let's write the mRNA sequence. Okay, you do it and then check with mine, okay? Seriously, check my work. I always make mistakes with these things. Okay, help me out here if you have it. LEU, yeah, okay. Yeah. Pro. LEU, right? And then it doesn't even stop, right? Normally, we're supposed to hit a stop codon, but because we shift the frame, we no longer have a stop codon in this new frame. And therefore, it just keeps on going. Okay, so insertion, and then it leads to frame shift, which leads to multiple missense mutation. Because all of them are wrong. I mean, I still have the MET, but basically everything else is wrong. Will there likely be effects?
Yeah.
Yes. Okay. This is a different protein. I don't even know if it's gonna work. And I don't even know what it will do. Do you want me to do one more or you understand?
One more.
One more? Good. Good answer. Hold on, I have to see which one. Yeah, you know what? Let's just do number 3. So this is what people actually do in real life. They take the DNA of quote normal people who doesn't have a certain condition, and then they collect DNA samples from people who have certain conditions, and then they compare it. They compare DNA and they find out, oh, sickle cell anemia is caused by a missense mutation. All right, go ahead and do this. I guess you also need the original sequence.
Wait.
Yeah.
For the one before, when you get to the end of like the amino acid sequence, when you put like for the A.
Yeah, so like nothing, right? Because yeah, we just go dot 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 because it keeps on going for now, right? Okay. What's the first thing you do when you get a sequence like this? You chop it up, that's right. Go, chop chop. What's the problem?
Oh, no, no.
No, I'm asking the mutation.
Sense.
Makes sense? Yeah.
ETA.
Mhm. I can't see it on the screen. Is it missense? Are you sure it's a missense?
If you write it out and it's still like, wait, met at the beginning, stop at the end, you do nothing is. Like it would be a mute.
That's right. Neutral, right? Right, because it's the same one, right? You see? Same one. So will there likely be effects? Nope. Okay, neutral. Is it okay? All right, I just have one last thing to teach you, and then you can go enjoy the sunshine. Okay, actually, let's do this question first. Okay, what do you think? Deleterious, yeah, most harmful. Which is the worst? That's what the question is asking. Okay. So quick. Which one is the nail in the tire? That's what I'm asking. Okay. So fast. How did you guys figure it out so fast? Because what? Okay, so let's see. First one, deletion of AAA at the beginning of the gene. That's probably okay because you are losing how many amino acid? You're using 3 nucleotides, but how many amino acid? One, right? There's 3 nucleotides, 1 codon, 1 amino acid. So that's okay. One amino acid deleted. Okay. It could be bad, but probably not the worst. UAC to UAU, this is silent, right? I think it's silent. This is nonsense, but it happens near the end. Okay. This one is the beginning, which is like frame shift and everything, right? And this one, again, UAA is stop codon, and it happens at the end, so it should be okay. All right, very good. I feel like you've learned something. Okay, this is probably the hardest part of all these mutation stuff. I know I said that for all of the stuff, but it's true. So let's take a look here. And I'm just gonna use this table. It's the same thing, okay? All right. On the quiz, you will also have to create mutations from a strand. Okay, so I'm gonna give you a strand and I'm gonna ask you to create certain mutations. And there are multiple correct answers. Okay? So here, this is the coding strand. Coding strand. Notice it's like T now and not U, right? So we are actually doing the mutation at the DNA level now. Right? Again, mutation for it to be permanent, it has to be happening at the DNA level. So a couple of ways to do it. I mean, you don't have to change the whole thing. You can just choose one. Okay, so let's say this is coding, and then I'm gonna have my mRNA, and then I'm gonna have the amino acid here. Okay? It doesn't really matter. You can choose whichever one you want. Let's say I choose this one. Let's do CAG. It's coding. So what would the mRNA be for CAG? If we do transcription. C
CAG.
CAG, because coding is the same as mRNA, right? Okay. So then we can find out what CAG code for. CAG is GLN, right? Okay. You don't have to use this table. You can use your own, doesn't matter. Okay. And now what kind of mutation I want you to do? I want a missense mutation. So for missense mutation, I can just change the first one to something. Change to A. So now it's A, G, which is LYS. Okay. But don't forget, on the test, you have to make the change at the DNA level. So that means instead of a C here, it's going to be a what? We mutated it. We needed to change from a C to an A. So at the DNA, it is going to be an A, okay? Because coding is the same as mRNA. Okay, so if you change C to A, you also have to change C to A. Okay? Like I said, this is not the only answer. You can pick something else. You can pick AAT here. If it's AAT, what would be the mRNA? AA what? AAU, right? Because T becomes U, right? And then you can look it up and you can also. Okay. So multiple correct ways of doing it. I mean, to make it easier for me to mark on the quiz, maybe just stick with the second codon. Okay. I mean, you don't have to, but it's easier for me to follow.
So, like, on the quiz, do we still write out the whole thing?
You don't have to write the whole thing, right? You just have
Just
to
the mutation.
yeah, choose one to change. Okay, give this a try, please. So this one, you might find it easier to transcribe the whole thing. I mean, you don't have to, but you might find it easier to do so. Mhm. Sure.
Oh,
Which one?
I changed the second one
Uh-huh.
to UAG and then.
Yeah, that's it, right? You change the C to a U, and now you have a stop codon, right? But be careful. You have to do it on the DNA. And what letter would I use for the DNA? Yes. Okay. Yeah, because U is same as T, right? Sorry, what's that, mate? No, say. Did you say you want to change the last one? Yeah. Okay, so that's a common mistake. You do not change the last one. Like, I mean, it's already a stop codon, right? So it's supposed to stop at the end. If you change it to like, UGA or something, then it's not really a nonsense mutation because it's supposed to stop anyways. Okay. Having said that, is there another possible answer here? Can I make it stop somewhere else? Yeah. Third one. Same thing, right? I can change it to U. So you don't have to do both. You only have to do one. Okay. Almost there. Now it will be a little bit harder, but not that much harder, if I give you a template strand. Okay, give it a try. This is template. And I want a nonsense mutation. So mRNA first, because this is template, we're gonna have to do complementary rule, right? So AUG, GUC. Uh-huh. Sure, that's good. Now we want a nonsense mutation. So I need to change one of these things so that it becomes a stop codon, right? So third one, yeah. Third one, we can change it to U again, right? What does this have to be then? What would the change be on the DNA? A, that's right. Because it's template, right? So you gotta make the flip. Is there another location? How do I change the fourth one? That's right. We can change it to UAA. That's also stop, right? But what would it be? That's it. All right. So the first page and a half is going to be like this stuff on the quiz. The last one, and then we can go. This is coding again. And I am asking you to create a truncated protein. What is truncated protein? It's a nonsense protein. Truncated means shortened, right? The only way to get a shortened protein is to have nonsense. So, but listen, this is not just regular nonsense, right? It's not like we're doing base substitution. It specifically asks you to use an insertion mutation to create a nonsense. You have to add an extra nucleotide. Okay? Now, like some people try to be smart on the test, and then they just like add like an AUG into the sequence or something like that, okay? On the test, I will specifically say insert a single nucleotide or something like that. You understand what I'm saying? No. So people do this on the test. They're like, okay, I'll just add like TGA. That's a stop codon, right? That will create a nonsense mutation, right? Okay. But I'm saying on the test, I will specifically say create an insertion mutation by inserting one nucleotide. Okay, so like you cannot put the whole codon in. That's like the easy way, right? Okay. All right, I'll just do this one with you quickly. AUG, AGAA, UUC. Okay. So where should I put the nucleotide to make it soft? Where?
Put a U before the AA.
Put a U before the AA. There you go. Put a U before the AA. Right here. Put a U before the AA. Because now that's going to be UAA, right? UAA is the stop codon. Which means over here, I'm going to have to put in a T. Thank you. T. It's a DNA, right? Hold on. I want to show you a common mistake. Okay. First of all, any question? If you are easily confused, maybe plug your ears. I don't know. Like I'm always concerned about showing people what not to do because they end up doing it when I show them. But anyways, this is a common mistake that they do on the test. Okay. They do this. They put a U here. Okay. Because they're like, hey, UAA, that's a subcodon. But don't write this down. This is wrong. Okay. I'm going to tell you why it is wrong. UAA is a subcodon, right? But how come this doesn't work? Remember, ribosome reads nucleotides in triplets, right? So when the ribosome comes, it's going to read it like this. AUG. What's the next thing it's going to read? GUA, you know? It's not going to skip the G and go UAA, right? You understand?
Yeah.
That's why it doesn't work. Okay, so please be mindful of that. Okay, thank you so much for sticking around. Okay, see you guys on Thursday for the lab. Be on time.